So to get started, I want to show an example of the scientific method. I took this directly from Wikipedia, but it's actually pretty nice. It's a pretty nice and concise summary of what we should do when we're coming up with new kind of research projects. And we start with an observation or question. We do research of the topic area. We form a hypothesis. We test it with an experiment, analyze data, and report conclusions. And even if we're doing kind of an engineering-based project, still this thinking of the stuff that we're doing in a framework like this can help you a lot. So the first thing I'd like to talk about is identifying good research directions. And so I'm going to look at that from the observation/question perspective here. So if we think about why we do research, particularly why we do research on natural language processing, there's a couple reasons why. The first is application-driven research. And usually this is, I would like to make a useful system or make one work better. So, this is probably the great majority of NLP research. Then separately from that, there's curiosity-driven research, which is like, I would like to know more about language or the world viewed through language. And so this doesn't necessarily have to be immediately like a downstream application that users are using will immediately get better. It's more like we have a burning question that we would like to answer, and we want to answer it. So NLP encompasses both. Sometimes if you read a paper, you'll have something that's doing both, especially like analyzing the internals or training dynamics of a neural network to answer a curiosity-driven question and then applying that to come up with a better method that makes things work better. I would like to say, though, that it's kind of rare that there's a paper that does both of them really well. And so usually one of them is kind of the main focus. And I think you can be well served by choosing which one is your main focus, and then kind of the other might come as a additional bonus on top of that. So here are a few examples of application-driven research. So, for example, Ping et al., they proposed the task of sentiment analysis. So actually, there was a paper 22 years ago that proposed the task of sentiment analysis. It might seem very, normal nowadays, but there was a paper that proposed it back then. And they proposed sentiment analysis because labeling articles with their sentiment would provide succinct summaries to the readers. So they basically wanted to provide information to readers, and that would be useful. Another paper by Reddy et al. 2019 proposes a task of conversational question answering because an inability to build and maintain common ground is part of the reason why virtual assistants usually don't seem like competent conversational partners. So when you're talking to your Alexa or your Google Home or something like this, you might ask it a question, and then after you asked it a question, you ask it another question, but it doesn't go back to the context that you had before, and they wanted to solve this problem. So they proposed this data set for it. Dearman et al. Proposed a method for bottom-up abstractive summarization because neural network-based methods for abstractive summarization produce outputs that are fluent but perform poorly at content selection. So they had a problem. They had a task already in mind. They weren't proposing a new task, and there was a problem with the existing system, so they fixed it. And then Kudo and Richardson proposed a method for unsupervised word segmentation, namely sentence piece, because language-dependent processing makes it hard to train multilingual models, as we have to carefully manage the configurations of pre- and post-processors for language. So they tried to make things easier. So like you can see all of these things, like the first two are proposing new tasks to solve, and they're doing it from the point of view of creating something useful for users. The second two are proposing new methods. The first one is like improving accuracy. So this is the most common. Most commonly people say, I have a task that I want to solve. There's a problem with accuracy. I want to improve it. But you can also improve other things. So you can improve like convenience, or you can improve efficiency or other things like that. So all of those are, perfectly reasonable things. I also have some examples of curiosity-driven research. These are actually harder to find in the ACL anthology. It's definitely the minority case, but they still do exist. So for example, Rankin et al. 2017 asked, what is the difference between the language of real news with that of satire, hoaxes, and propaganda? So they were not attempting to create a system for fake news detection. That was not their goal here. Their goal was just to figure out what were the different linguistic characteristics, and they found that scientifically interesting. Maybe downstream that would be useful, but that wasn't the point of their paper. Another one, Cotterill et al. Asked, are all languages equally hard to language model? And so basically they wanted to know, are all languages just character strings? And so language modeling them is similarly easy? Or are there certain characteristics of language that make them easier or harder to model with the current architectures that we have? And so they didn't propose a new architecture. They didn't propose to improve anything. They just proposed to examine this question. And also Tenney et al., this is actually an extremely impactful work downstream, but they weren't improving anything. They just quantified where specific types of linguistic information are encoded in BERT. So they found that, for example, syntax was encoded better in the early layers, semantics in the later layers, and then if you go farther, you have other fine-grained things like pragmatic style information. So I think you can kind of see the difference between these two. Are there any questions about this? No? Okay, let's move on. So the next question, which I think a lot of people might be asking, particularly with respect to assignment 4, which requires you to come up with something novel to do, is how do we get research ideas? And the way we can do this is twofold. So one is kind of, we want to turn a concrete understanding of existing research's failings into a higher level experimental question. And the two ways that I normally characterize doing this are bottom-up discovery of research ideas. Or the way I characterize this is bottom-up discovery of research ideas. And this is a great tool for making incremental progress on existing systems, on tasks that we really care about, or expanding the scope of a task that we care about. So some examples of this would be like in assignment number 3, you let's say you're looking at the question answering performance of models, of multilingual models on different languages. And for assignment 3, you implement a couple multilingual models on different languages, you run them, you look at the results, and you identify that multilingual models are particularly bad at answering questions about named entities. And so now you have looked at the output, you have decided that that's a big problem, you can go in and improve it. So this is a great tool for incremental progress. And like, in fact, doing this really effectively has been very effective in my own research career. Like if I feel like I like to look at data, I try to do that a lot. And by doing that, I identify the most frequent problems. And because of that, when I fix those problems, my accuracy goes up a lot more than people who pick the less good problems, right? And so if we want our accuracy to go up, I'm more efficient at, improving things. On the other hand, there's something from the opposite direction, is moving from a higher level question to a lower level concrete testing of that question. So this could be top-down design. This is top-down design of research ideas. This favors bigger ideas, but these ideas can be disconnected from reality, or they could be not solving the right problems. So the typical, like, very, very successful example of this is neural machine translation, or something like this. Neural machine translations, neural sequence models. This came out of a few people like Jeff Hinton and Yashua Bengio believing for a very long time that neural networks were the right way to solve lots of problems, despite the fact that there wasn't like super concrete evidence of that for a long time. And so they had this idea, which was like, we should be doing things with neural networks. And they successfully executed that, and now everybody is doing things with neural networks. So they made a really huge revolution in the research space. That's great. That's a great example of a successful top-down idea. But the problem is, for every example like that, there's 1,000 top-down ideas in the graveyard of not being very, effective. So I think in order to do something like this, you better have a very strong conviction, or you better have maybe some initial evidence or a very strong intuition about why this might be a good idea. And you would be able to test that intuition through intermediate steps to demonstrate, like through toy data or other stuff like that. Cool. So these are kind of the general ways that we can come up with research ideas. The next thing that we want to do is research our topic area. Were there any questions about bottom up versus top down? I'm going to talk about effective strategies to bottom up stuff in 2 weeks. So we can talk more about that then. But... Okay, if not, I'll move on. So next, we have research topic areas. So this is about how you will do assignment 3, which is researching a topic area, forming a very good understanding of the topic that you're trying to handle. And so there's a bunch of different ways you can do this. The first one is keyword search. And so you look something up on Google Scholar or something, finding older and newer papers. So this is like following the tracks of papers. You can read the abstract and intro, read the details of most relevant papers. And I don't do this as much now, but when I was a graduate student, I would often make a short summary of the paper to make sure I really understood the details. Because also now I teach a class, and actually making these slides is very useful for me. So going back into the transformer slides, that kind of serves as my, my way of digesting papers and making sure that I can explain them. And if you're not teaching a class, then you can go in and make a summary and do it yourself. So that can confirm, solidify your memory and like confirm your ability to understand everything that's in there. Cool. So next I'd like to talk about some sources of papers in NLP. One really good source is the ACL anthology. Another good source is Google Scholar. They both have their advantages and their disadvantages. Increasingly, actually, I realize now that I should add this to my slides, but increasingly, a lot of good papers in NLP are also published in machine learning conferences. So like ICML or NeurIPS or iClear or things like that. The problem is the ACL anthology is way better than any of them at like organizing the papers in an easy to process way. So I think I'll talk about this for now. And so the ACL anthology covers many prestigious venues in NLP. It has all of these ones here. This figure is a little bit old. I made it in 2021, but it reaches up to the present day. And what I do often is I can start with the past 3 to 5 years of several top venues in here, like ACL, EMNLP, NACL, and TACL, and go in and do keyword search. And so, like, let's say I was interested in multilingual large language models and evaluating them or some way. So I would go to ACL, and then I would just put in multilingual. And you get a wonderful paper by some researcher named Graham Neubig. That was not intentional. I didn't know that was going to happen. So on the fly cross-lingual masking for multilingual pre-training, scaling multilingual corpora and language models to 500 languages. That seems pretty relevant. Evaluating multilingual compositional generalization. So you can just go through here and see a bunch of papers that that could be useful. And you could, if you're doing a more machine learning oriented thing, you can do the same thing for like the NeurIPS proceedings or the ICML proceedings or something like that. Separately from this, you can go through Google Scholar. This allows for a search of papers by keyword. And so if I write like neural entity recognition, it will give neural architectures for named entity recognition, all of these things like this. You can view the more recent papers. So like, for example, if you're researching a kind of generic topic that a lot of people use, a lot of people do research on, you might be getting papers from like 1998 or something like this. And, they might be useful, but honestly, the methodology has changed so much since then that most methodological papers from that long ago are probably not going to be very useful. So you can view the recent papers. Another really useful thing that you can do is view papers that cite the current paper. And you can even click on this, and then you can search within the citing papers. So like, let's say I want to know about how people do. Let's say I want to see if anybody does neural entity recognition with state space models. So I do like state space model. And then I search within the citing articles, and I'm able to find 3 articles that at least cite this paper and talk about state space models. So none of these seem particularly relevant to what I was looking for, but you get the idea. Like this can be a useful tool for finding more recent things. And then finding older papers, this is also relatively easy. So you read the papers that you're interested in, and then it will have backlinks to older papers, and you look them up in the references. This is how I find older papers that might be relevant. And so these are the tools that I use. So I'd like to give a few caveats about Google Scholar and things like Twitter or LinkedIn or something like this. They give you very biased views on all the papers that are out there because they sort for popularity, basically. So actually, if you're looking at like Twitter or LinkedIn or something like that, you can actually get a pretty bleak view on natural language processing and say, all anybody is doing is training large language models because, these things tend to become, popular, and then they get amplified by algorithms and stuff like that. When in fact, like the landscape is much richer, which is why I do definitely suggest that you like actually look through conference proceedings and stuff and find papers that are not, amplified as much. So I definitely highly recommend doing this in addition to, Google Scholar or social media or other things like that you might be following. Cool. I'd also like to mention a thing about the ups and downs of preemptive surveys. So surveying extensively before doing research has a bunch of good sides. So it prevents you from duplicating work. So somebody else might have done a very similar thing. It also increases your toolbox of methods. So, if it's a problem that a lot of people have worked on before, then, it helps give you ideas of methods that you could be using. However, in a way, it also kind of constrains your thinking. So if you like, once you have built up a very extensive survey of like ways to do things, you tend to like move away from there when in fact, like if you just thought of ways to solve problems without looking at everything, you might come up with something over here. It might actually be a good idea, right? And so there's this really nice essay. It was actually shared with me by Chris Manning from Stanford. It's called How to Build an Economics Model in Your Spare Time. It's from a Nobel Prize winner in economics, but he's talking about how when he tries to come up with new and like important ideas, he doesn't look at economics journals, he looks at the newspaper and tries to, like look at problems that people are talking about in the newspaper and think about whether there's an economic solution to them. And so if we think about the analog of how we can do this in natural language processing, maybe you don't necessarily right away want to do a really extensive survey. First, you might just think about like what's bothering you. Like when you're using ChatGPT, what is really frustrating to you about how it gives responses? Or What are the things you wish it were possible to do through natural language processing, but are not possible to do? And then you can start from there. You can look at, what companies are doing in their tech demos, because the tech demos might be nice, but they almost never work as well as the tech demo makes them seem like they work. So that could be another place to get ideas. Or you can look at papers in a related field like machine learning. Like, let's say you're a machine learning oriented person and you really love like math and stuff like that. It's like, well, there's this good mathematical tool that I think could be applicable to a certain problem in NLP or something like that. So you could do that too. The final one, comes with all the caveats of doing top-down research, of course. So, you need to make sure that that really is the correct tool for whatever you want to solve. But definitely, this is something to think about. However, for assignment 3, you need to do a survey. So I'm forcing you to do a survey for assignment 3. So if you're going to do something like this, you can do it before assignment 3 and start thinking about what you want to be doing. So it's something. Any questions or discussion about that part? This is hard. I'm happy to discuss either now or in office hours or anything like this. But... Okay, cool. So the next thing is a form hypothesis. So once you have a general idea of what you want to do, and you have done a survey of related work, you can devise a final research question or hypothesis. And so a research question is one or several explicit questions regarding the thing that you want to know. And this is actually pretty hard for people. Like, I ask people to write research questions, and very often they don't write research questions in this format, and I have to ask people to try to change them. And what I think they, in general, should be are yes/no questions. So yes/no questions, and you have a hypothesis about what you think the answer to the question may be a priori. And that hypothesis should be falsifiable. So basically, it's if you get a certain result, you can demonstrate that the answer to this question is probably yes. If you get a different result, you can demonstrate that the answer to the question is probably no. And just to make this a little bit more concrete, I can give a few curiosity-driven questions and hypotheses. The curiosity-driven questions are a little bit easier. So we have the curiosity-driven question of, are all languages equally hard to language model? And they say, it is unlikely that all languages are equally easy or that methods are equally good at all languages. So that's their hypothesis. So they think a priori that that's the case. But that might be falsified by getting a very strong result that says, like, no matter which language you're modeling, many models that we use get similar results on them. What makes a particular podcast broadly engaging? So this was an analysis of podcasts where they compared popular podcasts and unpopular podcasts, or engaging and unengaging podcasts. And it says tips such as reducing filler words and disfluencies or incorporating emotion are things that people had anecdotally written on the internet as tips to make a good podcast, but nobody had actually empirically validated that. So they wanted to actually go and invalidate that. So they came up with hypotheses, and they could demonstrate that those had good or bad correlation with the podcast being judged as engaging. Application-driven questions and hypotheses are a little bit harder. So here is an example. This is an example from a paper that I wrote previously, which was where and why, or how and why do pre-trained word embeddings help neural machine translation? And this was back when pre-training was mostly like word embeddings. We weren't pre-training the whole body of the neural net. So now the answers to this question are a little bit different. But basically, the questions that we asked is the behavior of pre-training affected by language families and other linguistic features of source and target languages? So we expected that the answer to this would be yes. It would vary across them. Do pre-trained embeddings help more when the size of the training data is small? We expected that this would be yes. How much does the similarity of the source and target languages affect the efficacy of using pre-trained embeddings? We didn't have a hypothesis about whether it would or not. And is it helpful to align the embedding spaces between the source and target languages? We assumed this would be yes. And do pre-trained embeddings help more in multilingual systems as compared to bilingual systems? And we didn't have a good hypothesis about that a priori. Another one is, although recent study, the research question of whether and how contextual information benefits end-to-end speech translation has received little attention. And so their guess was that it probably would help. So application-oriented questions are a little bit tricky because the obvious one is like, does X make Y better? And so you have a method, you think it's going to make the output better. And so that's kind of your obvious research question. But the problem is the above question or hypothesis is natural, but it's very indirect. So normally you also have a hypothesis about like why it will help or something like this. And so if the answer is no after your experiments, why is the answer no? It could be that your original assumption about why a particular method would help was wrong, which is the worst case scenario, but you also could just have a bug in your code, or your data set, your test set might not be large enough, so you wouldn't be able to get a statistically significant result based on the amount that it helped you improve, or other things like that. So what I like to do in this case is try to come up with the intuition about why X will make Y better. And can you think of other research questions or hypotheses that confirm or falsify these assumptions? So some things that you can do are come up with like toy data, or come up with a subset of the data where you think this might be correct. So just to give an example, let's say we have a translation model and we have a hypothesis that improving entity translation in low resource languages will improve translation accuracy. And we run an experiment, or actually maybe this is an even better one. We have a hypothesis that incorporating contextual information in speech translation will help translation results. So incorporating context in machine translation has been a very old topic. Like people have been trying to do this for a very long time, but for a long time, the conclusion was that it essentially wasn't helping translation. People would incorporate context through neural networks or other things like that, and it just wasn't improving the results significantly. And in the end, the reason why was because there just weren't enough examples where contextual information was useful in the data sets that everybody was using. So people were using really long news sentences to try to figure out whether context was helping. But really long news sentences have so much information included in them that you can mostly translate sentence by sentence and get it right like 95% of the time. So the problem wasn't that any of the methods that people were proposing were bad. It was just that they weren't effective enough to see big enough results. And so then people changed the data set to like conversations or something like that. And in conversations, they're very contextual. You have very short utterances. And once you started doing things like that, then the same methods, like exactly the same methods were helping when they weren't helping before. And so the underlying assumption about incorporating context information is that context will be helpful, or context is necessary to, do translation well. So does anyone have an idea about how you could like actually verify that assumption? Any idea? Yeah.
Simplest way would be to just get an eval data set and then have a measure of, okay, if it improves more than X%.
Mm-hmm. And how would that verify the assumption that context is necessary?
So we're asking the question whether context is helpful in the class that we're doing now.
We're asking whether, so we're asking kind of a two-part. The main question is whether context is helpful given a particular, experimental setup, right? So like training data set, modeling method and training algorithm and evaluation algorithm. That's kind of the big final result that you want to get in your paper. But there's kind of a sub-question, which is context even necessary to translate well?
You train a model with context and one without context, right?
You train a model with context and one without context. But what if your model of context is really bad?
Okay, you have the same model architecture.
You have the same model architecture, but let's say your model architecture is really bad at capturing context. So then maybe it's a problem with your model architecture and context is necessary or helpful, but your model just isn't very good at capturing it. Yeah, exactly. So this is one thing that people can do. So there was an interesting paper. Let me see if I can find it. So this is a paper from a long time ago where they did something like this. It's evaluating machine translation systems with second language proficiency tests. And basically what they did is they had these English proficiency tests for, I think it was like middle schoolers or high schoolers or something like this. And then they used machine translation systems to translate them into Japanese, and then they asked Japanese students to solve them in Japanese. And so what they did is they asked anonymous system G and anonymous system Y, which are Google and Yahoo, and a human without context and a human with context to translate them. So they asked humans to translate each sentence without giving any context, and they asked humans to translate each sentence with giving context. And what they were able to find was, in this case, humans with context, the Japanese students were able to answer the questions most of the time. Whereas if they translated without context, like G and Y were doing at that time, actually Y was almost as good as human translators at, achieving the task here. So, but basically, like the important thing here is they were able to confirm their, idea that in this case, humans with context were much better than humans without context. So that would verify your like sub assumption, right? And so this is just like one example. This is just one example of something that you can do. But the basic idea is like your final result is that you want to build a system that does better on some benchmark that you care about. There's a bunch of things that go into whether it does better or not: your evaluation system, your model, your training data, your evaluation data set, and things like that. So can you break that down into sub questions that you could ask where you could verify that it's working or not, based on whether those things are happening? Another thing people do in ML-oriented things is create a toy data set where they know the phenomenon they're interested in exists and train their models on that and make sure that they work there. So that's another thing that you can think about. Cool. Any questions about this? Okay, sounds good. So the next thing is running experiments. So in order to do this, you'll find data that will answer your research question, run experiments and calculate numbers, calculate significant differences and analyze effects. Oops. And so this is a basic pipeline that we want to follow. So obtaining test data. So in order to obtain test data, we would like to find data sets. So if you're building on previous work, the safest thing that you can do is start with the same data sets. If you're answering a new question, you can think about, can you repurpose other data sets to answer the question? So very often there will be a data set that is appropriate for answering your question, and you can go and find that. Actually, our wonderful TA VJ has created a system called Data Finder that will automatically find it for you. So if you want to search for data sets, you can use his system or ask him about it. But if no appropriate data set exists, you can create your own. And particularly if for industry use cases, it's very common that you need to go in and create your own. Or if you're planning on doing research in academia afterwards, very often you'll come up with a research question where no data set exists, so you'll have to create your own anyway. So this is something that's really important to be able to do well in most cases. So I'll be talking about how to do all of these. So data set lists. The best one, I think by far in natural language processing nowadays is Hugging Face data sets. There's also other data resources like LRA is another one kind of by the more traditional natural language processing community. There's also the LDC, the Linguistic Data Consortium, and there are some older, heavily annotated data sets that are only available through those. At CMU, you have the ability to download things from LDC. So if you find an LDC data set in any papers that you're doing or online, you need to register for that. And I'm the person who's in charge of it, so I'll give you access and then you can use it. There's also things like Papers with Code, and Papers with Code basically automatically extracts kind of like the names of data sets. So even some things that don't appear on a Hugging Face will appear there. So annotating data. When you annotate data, you first need to decide how much to annotate, sample appropriate data, create annotation guidelines, either annotate yourself or hire and supervise annotators and evaluate quality. So a very common problem that a lot of people ask me is how much test data do you need? And I'm going to talk about statistical significance tests in a second, but basically you need to have enough to have a statistically significant difference between methods. And the way you do this, actually, sorry, very quickly, let me check. I rearranged my slides and I want to make sure that I didn't accidentally remove the slides on statistical significance, which would be a problem. Okay. Sorry, hang on one second. I just realized that I don't have the slides for statistical significance on this presentation. So let me grab them from the last class. Because this is pretty important. Okay, so yeah, let me explain statistical significance here. So basically, when we're doing statistical testing, let's say we have two models with similar accuracies. And these models with similar accuracies, let's say model one is a generative model, model two is a discriminative model. And we say on data set one, we have this result, on data set two, we have another result, on data set three, we have another result. And so then the question is, how can we tell if the differences are due to consistent trends that will hold on other data sets, or if they are kind of random noise due to the fact that we have one, due to the fact that, you know, data sets vary, models vary. And so the way we do this is through statistical significance testing. So I'm going to cover this briefly in this class, but you can see a drawer et al. For an overview, and also we're going to have a recitation on how to actually run statistical significance tests. So you can take a look at that there. And so the basic idea is, given a quantity, we test certain values of uncertainty with respect to the quantity. So number one is a p-value. And the p-value is what is the probability that a difference with another quantity is by chance. And so a lower p-value means more likelihood of having a significant difference. Usually the threshold for saying that we have a significant difference is there's a 5% chance, 0.05, that this difference between the models was due to chance or like data sampling or things like that. So p less than 0.05 is kind of a threshold for significance. Another thing that we can measure is confidence intervals. And the confidence interval is what is the range under which we could expect another trial to fall? And I'll talk about both of these. There's another concept called paired versus unpaired tests. And an unpaired test, this means we compare the means of a quantity on two unrelated groups. So an example could be the test of the significance of a difference of accuracies of a model on two data sets. So like, let's say I have data set number 1 and data set number 2. What is the likelihood that there's actually a real difference in the data sets as opposed to just random sampling noise between them? In contrast, a paired test compares the means of a quantity on one data set under two conditions. And so an example of this could be testing the significance of a difference of accuracies of two models on one data set. So this is a really important difference. And the reason why it's a really important difference, well, number one, we're most commonly interested in the latter. Number two, if we can make assumptions about the association of the points in a data set, we're much, much more likely to get a significant result because we can look at the difference of the models on individual data points as opposed to looking at just the difference in the means. So one example of a statistical significance test is a bootstrap test. And the bootstrap test is really convenient because you can implement it for any evaluation metric that you want to be using. And so in NLP, we can use lots of different evaluation metrics. We can use an evaluation metric like accuracy, but we can also use an evaluation metric like F measure for classification, or BLEU score, or character F score, or word error rate, or something like that for various tasks. And this is applicable to any metric you want to use, any quantity you want to measure also. So the basic idea of a bootstrap test is a method that can measure p-values and confidence intervals by resampling data. And so the way you do this is you sample subsets from your dev test set with replacement. So you might sample 10,000 times, and you measure accuracy on these many subsets. And then you look at all of the accuracies that you got on these subsampled data sets. And then you take the middle percentile range, like 2.5 to 97.5, and you can treat that as a confidence interval, the 95% confidence interval, about where you're like 95% certain that your results will fall in here. Another thing that you can do is you can do a paired test. And what the paired test does is it measures the number of wins and you measure the percentage of wins. And this is the confidence that a gain in accuracy is not by chance. And so this could be 1 minus the p-value of the paired test. So this is easy to implement, applicable to any evaluation measure, but somewhat biased on small data sets. Maybe I can give a more concrete example. So let's say we have a classification data set. What you can do is, let's say we have A, B, C, D, E, or X1, X2, X3, X4, X5. So this is our classification data set. And we have system 1, system 2, and we have right, 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 wrong, right, right, wrong, wrong, right, or something like this. And so what we do is we randomly sample a sub data set. And let's say this is like X3, X2, X4, X1, X2. And so this is our sub data set. What we do is, so X3 would be 0, 1, X2 would be 1, 1, X4 would be 1, 0, X1 would be 1, 1, and then X2 would be 1, 1. And so the overall accuracy here is 60%. and 80%. So if we didn't do any statistical significance tests, we might say, oh, system 2 is better, obviously. But if we do the significance test, this is one sample from the bootstrap test. In here, now we get like 80% and 80%. And it's like, okay, actually, maybe in some cases, these systems are equally good. Maybe there's a tie. Or if we sampled another one, let's say we sampled X4, X1, X2, X4, X1, then we would get something like 1, 0, 1, 1, 1, 1, 1, 0, 1, 1. This would be 100%, and this would be 60%. And so in some cases, depending on how we sample, actually system 1 wins. And so you count the number of times that system 2 wins based on these subsamples. You count the number of times that system 1 wins, and you count the number of times you get a tie. And only in the case where system 2 or like the better system wins more than 95% of the time, do you say that there's a significant difference between these. Or alternatively, you could also look at the confidence intervals by saying, okay, I sampled like 95% of the time, the accuracy of system 1 is like 80% or lower. And so that would give you the upper bound for confidence. So yeah, sorry, this is a very, very quick overview of this, but the reason why this is useful is, let's say you create a very small data set. If you create a very small data set, this is going to give you it's going to be very hard to get a statistically significant result on this data set because it's tiny, right? And, you know, quite frequently you're going to be sampling data sets like this, where model 1 wins. Quite frequently, you're going to be sampling other data sets where model 2 wins, and basically you're not going to be able to say with confidence which model is better because you just don't have enough data to say that. But as you make your data set bigger and bigger, it becomes easier and easier to get a significant result. And so because you're more sure that you didn't just randomly pick data that model 2 is better at giving you this result. So there's also other varieties of tests. There's things like t-tests for unpaired outputs and paired t-tests for paired outputs. Those work when your outputs are additive. So they work for accuracy because the accuracy is just you add all the ones and then divide by the number of instances, and that gives you an accuracy. That doesn't work for something like F measure. Because F measure is 2 times precision times recall divided by precision plus recall. In precision and recall, you can, like a t-test works for this, but there's a non-additive component of F measure, so you can't calculate statistically significant differences in F measure using a t-test. In that case, you have to use a bootstrap method like this in order to get it to work, or you need to do some really complex math, but I'm just using the bootstrap method. Cool. Are there any questions about this? I guess we'll have a code example in the recitation, so you can go in and take a look at that. There's also tons of code examples online. Is that okay? Okay, sounds good. So now let me go back to the actual slides for today. And given those the results about statistical significance, how can we estimate how much testing data is enough? And there's a method called power analysis that allows you to do this. And basically the idea of power analysis is that you make an assumption about the effect size between settings. For example, the expected accuracy difference between tested models. And given the effect size, a significance threshold, you can determine how much data is necessary to get a significant effect in most trials. And so to give an example, again, let's say we're talking about the accuracy. Let's say we have a baseline model and we have a we have a baseline model, and then we also have our proposed model. And we know kind of from experience that the baseline model is probably going to get around 90% accuracy. We know by like eyeballing the data or something like that. And then we think our model is going to get 93% accuracy. And we want a significance threshold of p is less than 0.05. Given these two quantities, you can basically go in and say, okay, now we need 500 test examples in order to say with confidence that we will be able to distinguish between two models with 90 and 93% accuracy. And I can show the algorithm that they have in this paper. But basically the way this works is you sample a data set, compute the effect of interest on the sample, compute the p-value, and then you can calculate the power by basically checking the number of times that the p-value is less than your threshold, multiplied by the fact that the sign is in a particular direction. And by doing this, you can essentially calculate how much data you would need. Or sorry, you can calculate the statistical power, and then you can do this for various sizes of data sets. So you can gradually increase the size of the data set or decrease the size of the data set. And that allows you to figure out how big your data set needs to be in order to get a statistically significant effect of the various sizes. And so like many people ask me the question, like, how big of a data set do we need to make? This is basically the statistically, like, quote unquote, correct answer for how you can do this. And also for assignment 2, we're going to ask you to justify your choice of creation of a data set of a particular size for testing based on this. So pay attention and please look at the references here, and you should be able to pick up that. Cool. Any questions? I didn't go like really deeply into the formulas here. You'll probably have to look them up in the paper, but hopefully that gives you the general idea. Okay, next. How much training data do I need? So in general, more is usually better if you're fine-tuning a model. So I can't tell you like you don't need to make more data, because probably you do if you're not happy with your performance. But recently, you can get very reasonable performance with few-shot or zero-shot or pre-trained models and prompting. And because of this, in some cases, maybe the answer is 0. Maybe you don't need any training data and you could just use a zero-shot prompted models. So you need to choose like what your accuracy threshold is. You need to decide whether you want to be fine-tuning a model to improve performance or doing other things like prompt engineering or other stuff like that. So basically, there's no correct answer to this. One thing to be aware of is sometimes if you select data intelligently, you can improve more quickly with something like active learning. And active learning chooses representative and difficult data that you can be using. So when you sample data for fine-tuning, what you want to be doing is you want to be sampling data that has good coverage of the domains that you want to cover. You also want to be covering, for example, languages or language varieties or demographics of users. And another thing is when you're doing this, it's often a good idea to document how you're creating data. And there's this paper, Data Statements for NLP by Bender and Friedman, which suggests a bunch of different things that you can use to document your data collection and like why and how you collected the data. And this gives you some pieces of information that could be useful. This has been incorporated into the Hugging Face datasets dataset cards. And now Hugging Face datasets actually has lots of metadata that's kind of inspired by this, although it's been adjusted for more kind of like practical industry use cases. Another thing is annotation guidelines. So if you're asking humans to do anything, or for that matter, if you're asking GPT-4 to generate data for you, you need to tell people or GPT-4 in a clear manner how you will like how it should be creating data. So the first thing is if you try the first thing that you can do is you can try to annotate yourself. And if you actually try to solve the annotation task yourself, then you'll realize that there's lots of corner cases that are hard to decide on, other things like that. So like if you're annotating sentiment, what is the boundary between very positive and positive? If you're annotating question answering, like for example, do you want to answer in a whole sentence or do you want to answer with only a short, concise answer? Like these sorts of things you'll need to tell either an annotator or a model that you're asking to do annotation. To give some examples from Penn Tree Bank, part of speech annotation guidelines, this is very old, it's from 1990. But basically they have like adverb, this category includes most words that end in ly, as well as degree words like quite, et cetera, et cetera. It has other things for adverbs. And then it has like confusing parts of speech with examples. One thing that I found like really, really interesting is like if you look at these annotation guidelines, it's like prompts. So if you look at this, it's like these are your prompts, your zero-shot prompts, and these are few-shot examples. So like even for humans, we were doing few-shot prompting with examples when they were doing annotations. So it's kind of fun. Hiring annotators. So like, let's say you want to actually build a data set and pay people to do things. For smaller scale projects, very often you can just annotate yourself and that's fine. There's a fixed set of overhead to get other people to do something and train them and stuff. So, I often just annotate things myself. You can also find friends or other students or coworkers who can help you out with things. You can bribe them with pizza or whatever favorite food or beverage that they like. Then for finding people online, there's a lot of things that you can do. I very often hire freelancers through platforms such as Upwork. This is good and bad. The bad thing about it is that this is often more expensive. The good thing about it is you get people who have pride in their work and accountability and motivation. Because like if they get rated poorly, it's going to be harder to get work, and often they're professionals in their fields. So like if you want to get a code generation data set, you can hire good freelancers. I've actually heard rumors that people like OpenAI, they hire people and pay them $60 an hour to do this annotation because they really want people who are very professional and do a very good job. I don't pay that much. But I do pay well more than minimum wage, and I pay a competitive price for these freelancing sites when I get people to do that. Another thing you can do is crowd workers, and could be through sites like Mechanical Turk or Prolific or other things like this. So that's another option. Here, quality control becomes very difficult, and we're getting to the point where, number one, if you aren't very careful with quality control, language models actually do a similarly good job as crowd workers. And number two, all the crowd workers are using GPT-4 anyway. So you do need to be careful about that. One thing that I often do is I hire for a small job first to gauge timeliness and accuracy, and then hire for a bigger job. So just hire people to do 50 examples or 20 examples first, and then if they do a good job of it, then I hire them to do 200 or 1,000 examples. One thing to note is that if you're doing research in a university, you might need to get approval from an institutional review board. And this is in particular the case for subjective tasks. So this is when you're asking people how do you feel about this output? Do you think this output is representative of your beliefs or things like that, where it doesn't have a correct answer, a yes and no answer? If it's something like it does have a yes and no answer, which is like, how many verbs are in this sentence? Or how do you translate this sentence into another language or something like that? Then you don't need an IRB approval. But if it's borderline, you might want to check anyway. So that's something to be aware of. Next is assessing annotation quality. So one of my favorite ways to do this is assess human performance. And so the way we do this is you double annotate some data, and then you measure whatever metric you want to measure for machines, just with respect to human agreement. And so for translation, if you're using Blue Score or Karaf Score or something like this, then you would want to use this for assessment of the outputs. The advantage of doing this is that you get a human quality score, and the human quality score is directly comparable to the machine quality score. And so you can say, well, humans got the task right 90% of the time, and GPT-4 got the task right 16% of the time. So humans are way better than GPT-4. Or, humans got it right 80% of the time, and GPT-4 got it right 78% of the time. So this task is, this task, or maybe not necessarily the task, but at least the data set is more or less been solved by the strongest language models, and now we need to catch up open source models to the strongest ones or something like that. There are things that you can measure. You can measure things like kappa statistics. This is particularly useful for kind of just classification tasks. And what this tells you is this tells you how much higher is the agreement that you would get than if you got it by chance. And so, for example, let's say you're classifying spam, or you're classifying, toxic content or something like that. In 99% of your time, 99% of the time, the content is not toxic. In 1% of the time, the content is toxic. And then you hire some annotators and you get 98% accuracy. That's kind of bad, right? If you just said not toxic all the time, you would get 99%. What the kappa statistic does is it accounts for this, basically. It says, how much more likely is this than chance? And if you just had chance accuracy, you would get 0. If you had perfect accuracy, you would get 1, and you normally get something in between. So if it's low, you may need to revisit guidelines, hire better annotators, or rethink whether the task is possible at all or not. And some tasks are just impossible. Like if I'm asking, they're very hard for annotators. So like to give one example, annotators are really horrible at identifying fake reviews. And so like even if you hire annotators to identify fake reviews, they're bad at doing that. So you're not likely to get high agreement. Cool. I'm going to skip over this part because I already talked about it. Okay. Any questions here? Okay, sounds good. Next, I'd like to get into running experiments. So running experiments, one thing I find very helpful is workflow automation. And basically what I like to do is I like to modularize each step of an experiment into a directory where you have like a directory as input and a directory as output. This is my personal way of doing things. There are other ways of doing things that are also good, but very often, like just to give an example, you'll need to do pre-processing according to some, you'll need to do data selection. So you'll need to select which data sets you're training on. You'll need to do pre-processing of them with a tokenization model. And then you will need to run an experiment. And then you'll need to do evaluation. And those are all kind of like discrete steps where the data selection takes in your big pool of data and outputs a data set that's been selected. The tokenization will take a tokenizer model, maybe train a tokenizer model and split it up into different tokens. The training will train, it might output a whole bunch of checkpoints, and the evaluation will evaluate one checkpoint. And so those are all kind of modular. And you can actually think of each one of them as like a function in your Python program. And you kind of want to avoid rerunning data set selection and tokenization every time you do a new evaluation, right? Like that would be kind of silly. You definitely want to avoid rerunning training every time you evaluate a checkpoint. So what I do is I often name directories by parameters where it's like transformer layer 8, node 512, dropout 0.5, label smooth 0.02. And so I have all the parameters in there. And then the training process will output a whole bunch of checkpoints in here. And then for my evaluation, I have evaluation metrics and I have the checkpoint I'm evaluating. So when I do evaluation, I will then append checkpoint 6 metric F measure or something like that. And so I keep around all of the previous information and just append. And so this allows you to avoid rerunning things because you can just have your Python code check if the directory already exists and already has been completed, and then read in the result if it already has been, or run the experiment if it hasn't been. So you can write this in pure Python by just adding like some if statements at the beginning of the function, some if statements at some like output statements at the end of the function. There are more sophisticated methods. So there's like a toolkit called duct tape that was originally created here at CMU, and my student Patrick is maintaining now at this link. So you can either just roll something on your own or look into one of these more complex workflow automation things to save you time. Okay, evaluation. So I talked about this to some extent. So yeah, I'll just skip over that. And result reporting. For papers, one thing that I really like to do is plan the results section in advance, or at least imagine the results section in advance. So what I think of is like, what experimental claims would I like to make? How am I going to support them by the experiments that I'm going to show in the results section? And this identifies unjustified experimental claims. Like, so let's say your method is, you're saying something like, this method improves across a wide variety of languages, and then you realize that you only have one language in your experiment section. That's a problem, obviously. Also, I really enjoy like assuming that all of my experiments are going really, really well. And you know, none of my runs crash with CUDA out of memory errors, and you know, all of the experiments appear as expected. And if you do something like that, you can be ambitious and say, okay, how can I make this research project really impactful? Like, and another thing that I like to ask my students or people I'm working with recently is like, who are like 3 people in the world who will be really excited by your paper? Like, name actual people. And where do those people work? What do they care about? What sort of evidence would you need in your paper to make them really excited about your paper? Or something like that. And very often people will reply to me like, oh, I think people in Google will be very excited about this and they're going to use it. And I'm like, well, you're writing all your code in PyTorch and they don't use PyTorch. So how are you going to convince them to use your paper? They're going to have to re-implement it in JAX, and that's going to suck for them. So like, you know, what are the barriers for them actually using it? And then maybe the people are like, oh, well, maybe actually I don't want people at Google to use this and I can think of somebody else. And it's like, well, great. So now release it open source and people will have it open source. So you can kind of think about like the types of evidence that you would need to convince people to use your work, and that can result in your work being more impactful in the long run. And if you think about it from the very beginning, that also helps you plan your experiments. Like, what sort of evidence is necessary for people to get excited about it in the first place? Another thing that I like to do with result reporting is result generation scripts. So I often generate paper LaTeX directly from log files. There's 2 reasons why I do this. Number 1, it's efficient and minimizes errors. Number 2, it allows you to preemptively plan experiments that you want to run. So like, for example, if we go back to the directory that I talked about before, I can write a script that reads in 20 evaluation results from 20 different directories and fills in a table. And if that directory doesn't exist yet, it will put like TBD or something like that in the table. So I can very quickly see, okay, these things are TBD. Oh, this thing has been TBD for a very long time. Is my experiment crashed? Do I need to go back and like restart my experiment or something like that? So it's an efficient way. And when you finish the last TBD, it's a very good feeling also. Cool. Next, computational resources. Actually, I kind of already talked about this a little bit, but on Amazon Web Services, we have class credits that we're going to be issuing as soon as the assignment 1 deadline is over. There's also Google Cloud and Colab. You can get commodity GPUs and other things like that. So you can also consider that. Okay, let me get into data analysis. So I'm going to cover this a lot more in an interpretation lecture, and this is going to be in 3 classes. So this is going to be the Tuesday after next. Very important things, though, look at data. You'll want to do quantitative analysis and qualitative analysis. You can also look at model explanations. So I'm going to cover how to do all of these things in that lecture. I don't have enough time to do it today. Then the final thing is reporting conclusions. This is also too much for a single class, but I very highly recommend this lecture. Sorry, these lecture slides. They don't take that long to look through. They're maybe 20 minutes or so, but they're very, very helpful. They talk about how to structure a paper, other things like this. And if you follow this advice for writing your reports for like 3 and 4, assignment 3 and assignment 4, maybe even assignment 2, I think you can't really go wrong. Actually, 3 and 4 is probably better than assignment 2. Assignment 2 can be more descriptive. So definitely take a look at that if you go.